Okay, sorry for the technical problem. Let's go for part 2 of the fourth lecture. So what we were trying to do is calculate the expected value of the geometric distribution, which we can write as once we have gotten the probability function associated with geometric distribution, which is given by this, we can write this as this infinite sum. Now, the problem is how do we evaluate this infinite sum? Okay, so I'll show you two different ways. One is a bit more analytic, and the other one is perhaps a bit more probabilistic in flavor. So one of the things that we're going to realize here is that this p is outside the sum, so this is equal to p times the sum from k equals to 1 up to infinity of k of 1 minus p to the k minus 1. Okay, now this term here, we can actually realize that is minus the derivative with respect to p of 1 minus p to the k. Okay, so exchanging summation and derivative, this is equal to p times minus the derivative with respect to p of the sum from, in this case, would actually be k equals to 0, because the 0 term would still be included in this case, k equals to 0 up to infinity of 1 minus p to the k. Okay, so this can be done because the sum is absolutely convergent. Okay, so if the sum is absolutely, the sum of the derivatives and the original sum is absolutely convergent, we can actually put the derivative inside or outside the summation, and it doesn't change the result. Okay, so for this specific example, we would get that the sum, so this is the geometric sum from k equals to 0 up to infinity. So the sum from k equals to 0 up to infinity of 1 minus p to the k is exactly equal to 1 over 1 minus p, which is equal to 1 over p. So then minus the derivative with respect to p of the summation from k equals to 0 up to infinity of 1 minus p to the k is going to be minus the derivative with respect to p of 1 over p, which is equal to 1 over p squared. Hence, the expectation of x is going to be equal to p over p squared, which is equal to 1 over p. Okay, so for a fair coin, we need to wait two trials. So in this case, for a fair coin, this is p equals to 1/2. We need to wait 2 trials to expect to see the first heads. Okay, so basically, if I to be able to expect to see a first heads, and if we have a fair coin, we would expect to have to flip the coin at least 2 times. Okay, so the first one you would expect to have 1/2 probability, and then more than 2 times it starts becoming more and more unlikely. Okay, so this is one way of doing this. Another way of doing this will be writing x as the sum of a bunch of random variables. So let's, how do we write this explicitly? 1 second. Where I have my notes. Okay, so we are going to write x as a sum from I equals to 0 up to infinity of xi, where xi is a Bernoulli variable. It's a Bernoulli variable which indicates that the first success happens after round I. Okay, so so the expectation of xi is going to be the probability that the first success x happens after I rounds. Okay, but what is the probability of this? This is equal to the probability that we land tails I minus 1 times in a row. Okay, so having that the first success happens after I rounds is the same as saying that the first I minus 1 times I flip the coin, you get tails. Okay, so what is this? This is going to be 1 minus p to the I minus 1. Okay, and so you can actually check that this identity, because if x is equal to 2, then you realize that the first success happens after the first and the second round. So then that would expect the first x1 to be 1 and the second x1 to be x2 to be 1. And so then you get that x is equal to the sum of these two guys, which would be equal to 2. Okay, but now if we do the properties of the expectation, so we have the expectation of xi for every I. Now, the expectation, so what do we get? So now the expectation of x is going to be equal to the sum from I equals to 1 up to infinity of the expectation of xi, which is just equal to the sum from I equals to 1 up to infinity of 1 minus p to the I minus 1. Changing variables, this is the sum from j equals to 0 up to infinity, 1 minus p to the j, and this is just again equal to 1 minus p, which is equal to 1 over p. Okay, so this is another way of computing the expectation, which can be helpful now with computing the variance. So computing the variance, there is two ways of doing it. One way is by taking these derivatives, and I'll show you how to do that now. Okay, so now let's do the variance of x. So again, the variance of x is going to be the expectation of x squared minus the expectation of x squared. Okay, so this is 1 over p squared. So now we need to take the expectation of x squared. The expectation of x squared is going to be equal to the sum from k equals to 1 up to infinity of k squared times p times 1 minus p to the k minus 1. So the way that you can do this is by realizing the following. Again, you take the p outside, and now you write k squared. You write k squared as k equals to 1 up to infinity. This is going to be k times k minus 1 plus k times p, times 1 minus p to the k minus 1. So now what you should realize is that the following. You can rewrite this as saying this is p times 1 minus p. So here I have just rewritten this in a different way. This term we already know how to calculate. This term is the one coming from the expectation, which is going to be 1 over p. And then what you're going to get here is this is, I have taken a factor of 1 minus p outside, and this is going to be the sum from k equals to 1 up to infinity of k times k minus 1 times 1 minus p to the k minus 2 plus, and then this is from the expectation term, from the expectation sum. This term is exactly 1 over p. But this guy here is the second derivative with respect to p of 1 minus p to the k. Okay, so if you get this, this is going to be, again, doing the same computation as we did before. This is p times 1 minus p times the second derivative of p squared of 1 over p plus 1 over p. Okay, and the second derivative of this guy is equal to 2 times, this is equal to 2 times p cubed. Okay, so we get 1 minus p over p squared to 1 minus p over p squared plus 1 over p. So the variance of x is equal to 2 times 1 minus p over p squared plus 1 over p minus 1 over p squared. Okay, so let's try to put this all in the same denominator. So we are going to get 2 minus 2p plus p minus 1 over p squared. So here you are going to get 1 minus p times p squared. Okay, so this is another, this is one way of doing the variance. Another way of doing the variance, which will be a little bit more involved. Okay, so this is what I would call the analytic way of doing it. So realizing what is the derivative of what, this is the analytic way. And let's do the probabilistic way. It's basically realizing that you can write x equal to the sum of this xi, I equals to 1 up to infinity. So then Of course, you have to be careful with these expectations and these kind of things, but the point is that if everything is absolutely convergent, then you expect that the variance of x, so we want to take the expectation of x squared. This is equal to the expectation of the sum from I equals to 1 up to infinity squared. But this is the same as the point is that the square will hit the square terms. This is the sum from I equals to 1 up to infinity of the expectation of xi squared plus the cross terms. So the cross terms will be, so the way I'm going to look at the cross terms, let's say that here we have I and here we have j. We have the diagonal, and then the off diagonal are symmetric. So this product is these products are the same. So then instead of counting all of them with I different than j, I can count all of them such that j is less than I. Okay, so I can sum from I equals to 1 up to infinity of the sum from j equals to 0, j equals to 1 up to I minus 1 of the expectation of xi times xj. Okay, and here because I'm summing them twice, I put 2 here. Okay, so this seems like a lot involved for something that seems not so hard. So the point is that sometimes maybe you don't realize that there are these magic derivative things going on. So then the point is we can decompose these random variables as something simple as Bernoulli variables. And these Bernoulli variables now we can take the expectation of these guys and then start looking at the correlations. The nice thing about Bernoulli variables is that the square root of a Bernoulli variable is equal to xi. So the expectation of xi squared is equal to the expectation of xi, which is what we have said before. This whole term is equal to the sum from I equals to 1 up to infinity of 1 minus p to the I minus 1. So all of this is equal to 1 over p. Okay, so to get the expectation of x squared, we need to figure out what's going on with this term, the expectation of xi xj. So, but how had we define xi? Xi is the Bernoulli variable, which indicates that the first success happens after the round I. Okay, so then if, let's say that in this case I've taken j less than I, then if xj is equal to 1, sorry, if xi is equal to 1, this implies that xj is equal to 1. Okay, so because if the first success happens after round I, then this implies that the first success happens after round j for every j less than I. Okay, so for every j less than I, if xi is equal to 1, this implies that xj is equal to y for every j less than 1. So then, if j is less than I, then xi times xj is equal to xi. Okay, so this is just a realization that once you multiply these two Bernoulli variables that have this property, that one of the sets is contained inside the other, then when you multiply them, you get just this Bernoulli variable. So here, what we would have is plus 2 times the sum from I equals to 1 up to infinity of the sum from j equals to 1 up to I minus 1 of the expectation of xi. Okay, so this is the probabilistic way because you are sort of using and abusing the fact that these are Bernoulli variables. And now what we need to calculate is the sum. So what we have is this is equal to 1 over p, which is what we calculated before, plus 2 times the sum from I equals to 1 up to infinity of this sum that has I minus 1 terms. So I minus 1 times, so this should be I minus 1 times 1 minus p this would be 1 minus p to the I minus 1. Okay, and here, yeah, I'm not going to overcomplicate this. You can actually do a similar, you can do the decomposition the other way around and actually realize that this is xj, e of xj. So maybe what I want to do is sum the other way around first. So, I mean, the point is that you can actually figure out that this is going to be 2 times 1 minus p over p squared. But the other way of doing it, it would be to take, so instead of taking the sum from I equals to 1 up to infinity of j less than I, j then less than I of e of xi xj, we would need to take the sum from I equals to 1 up to infinity of the sum of j bigger than I e of xi xj, and in this case this would be the sum from I equals to 1 up to infinity of the sum from j bigger than I of the expectation of xj, and here we are using j bigger than I to use the same property as before, and here we would get that this is the sum from I equals to 1 up to infinity of the sum of j bigger than I, j bigger than I. So this is j equal to I plus 1 up to infinity of 1 minus p to the j. And now you can follow these calculations to get that all of this is going to be equal to 1 minus p over p squared. Okay? I'm not going to follow it, but the idea is the same of what we've been doing so far. Okay, so finally, let's go to the applications that we always been seeing. So I'm going to wave my hands a bit here because it's not quite clear that the things I'm going to say are completely justified, but it's a good idea to get it's a good idea to get why these things can be helpful and how using these types of properties we can figure out how to solve a problem. So let's look again at Gambler's Ruin. Okay, so here what do we have? We have a gambler that bets on a fair coin, that gains $1 for every head and loses $1 for every tail. The gambler will stop when he has accumulated N dollars of wealth, or he has gone bankrupt. Okay, which this is equal to $0 of wealth. Okay, so what we have looked before is, like we said, K. So if the initial wealth is K, then what is the probability the gambler wins? Okay, so what is the probability that the gambler wins? You can actually check that this is the probability of winning, so reaching N dollars before going bust, becoming bankrupt, is going to be K over N. Okay, so let's try to model this with random variables, okay? So let's say that Sn is equal to the wealth at round n, okay? So then Sn is going to be equal to S0, which is initial wealth, plus the sum from I equals to 1 up to n of xi, which these are, xi are independent variables, so they are independent random variables, such that xi is only takes the value minus 1 and 1, and the probability that xi is equal to minus 1 is equal to the probability that xi is equal to 1, which is equal to 1/2. Okay, so we have a fair coin. So okay, so now let's try to find a different way of finding the solution of the probability that our gambler will win before he goes bankrupt. Okay, so this is just to remind you of what I keep saying all the time. If this is the number of rounds, and this is wealth. We start with 0 is k, and here we have our desired value n. So if the number of values are here, each instance of this guy is what is called a random walk. Okay, so this thing here is a random walk. Okay, so this is one instance of one possible instance of what happened, and then there is depending as the number of rounds go higher and higher, the possibilities that can happen become larger and larger. They become so large that they are actually equivalent to the amount of numbers between 0 and 1. Okay, so let's consider Rn to be the value the wealth that the gambler has after n rounds. Okay, so but now why is this different from Sn? So Sn is the wealth around n, assuming I haven't won. Okay, so Rn is going to be equal to Sn if the game hasn't ended, is going to be equal to capital N if the gambler has already won, and it's going to be equal to 0 if the gambler has gone bankrupt. Okay, so all right, so now let's wave our hands a bit. Now, what's going to happen with Rn? So the point, let's try to think a bit about Rn. So let's say that we take the limit when n goes to infinity of Rn. So the point is that this should have only two values. This is going to be n if the gambler has won, and it's going to be 0 if the gambler has gone bankrupt. Okay, so this limit when n goes to infinity of Rn, so this is the limit of our sequence of random variables. The point is that now we have this R infinity, okay, which we have said this is the limit when n goes to infinity of this sequence of random variables, which we'll talk about limit of random variables later on, but more or less this is the idea. So one question that you could ask is, okay, but that's not quite true. It could happen that Rn never leaves n and 0, okay? So you could actually draw an infinite sequence of winning and losing such that the gambler has never won or lost, even in an infinite time domain. The point is, we're not going to do this right now. The point is that the sequence of those, the sequence of coins flips that would give that would have measure 0, okay? So the probability that you get stuck in this band is going to be equal to 0, okay? So you can actually show that R infinity will take the value n and 0 with probability 1. Of course, there are events in which R infinity would be a value between n and 0, but those we can actually think that they are actually not even relevant. Okay, so then what are we going to check? So the probability of winning, so the expectation of R infinity is going to be n times the probability. Okay, so let's write it. N times the probability of winning plus 0 times the probability of losing. Okay, so once you have written this in such a simple way, if we can actually compute the expectation of R infinity, we can use this formula, okay, this is equal to 0, to check what is the probability of winning. So just checking the expectation of R infinity is enough to determine the probability of winning. Okay, so how do we actually get the probability of winning? So here, how do we actually get that expectation? Here we notice that the expectation, what we would expect is the following. Let me get the limit of n to infinity of the expectation of Rn is going to be the expectation of R infinity, okay? This also needs to be justified. Okay, in this specific example, it can be justified because Rn are bounded, okay? And this is true because Rn are bounded. So if you have bounded bounded sequence of random variables that they have a pointwise limit, then if we consider the pointwise limit, then we can actually show that the limit of the expectation of Rn is equal to the expectation of R infinity. Okay, so this needs to be justified. I'm not going to do it in this class, but the main point is that because Rn are bounded, we can actually do this. Okay, but now the point is that for n rounds, maybe it's a bit easier of what is the expectation of Rn. So the expectation of Rn needs to be, well, it's approximately equal to S0, or in this case, K. And this is because we have a fair coin. Okay, so because we have a fair coin, then we would expect that the expected value of playing this game should not affect our wealth. Okay, so it's as likely as it goes up as it goes down. So then you would expect that this guy has an expected value approximately of K. So this is not quite true because, I mean, if you look at the graph as before, let's say that we start, so this is n, and let's say that we take k, which is equal to n minus 1. So if we win in the first round, then from there on, we are stuck with value n. So then, once we do another step, the wealth, so here this would be Rn, and here is the number of rounds. Okay, so this is 1, this is 2. So for the second round, if I have flipped the first heads, I will stay with n. If I heard tails, I will get to n minus 2. Then we would go to n and n minus 3, n minus 1 and n minus 3. And then again, this would actually separate. into this guy, this tree, for round n is equal to 3. So what you can actually check is that if you do this, if you follow this procedure, then we do not get that the expectation of Rn is different from k, but the limit when n goes to infinity of the expectation of Rn is actually equal to k. Okay, so this is creating a sort of, the fact that you're putting a ceiling here is creating an anti-symmetry, but once you are actually going to get the same symmetric behavior once you get to 0 here. Okay, so then you're actually even out everything that's going on, and we can actually show that the limit of E of Rn is equal to k. So then at the end of the day, what we're going to get is that k is going to be equal to E of R infinity, which is equal to n times the probability of winning, which implies that the probability of winning is equal to k over n. Okay, so then this is another like sort of more heuristic reason why the probability of winning is k over n, by using just the properties of expectation. Okay, so the idea of understanding expectation and its properties well is that it can actually save you a lot of trouble when you're trying to get some idea of what's going on in a specific problem. Okay, thanks.